Hello, it's Keith here, and this is the first of my x86 assembly programming tutorials. Now, I've done a Z86, 502 and 68000 series in the past, but this got me interested in the other platforms, and so I thought we'd start doing a bit of exploration with the x86. Now, of course, the x86 is the foundation for all of the processors we have today, the x86 range and the x64 range. So the current processor you're probably watching this series on is actually based on the history of the x86. Of course, unless you're watching on a phone, in which case you want to watch my ARM tutorials, which will be starting very soon. But anyway, you get the idea I'm making. So we're going to be covering the x86 and also the 8186, and we're going to be doing this in DosBox primarily, because that's a great way of writing a few little programs with x86 and not worrying about damaging our real machine because we're protected by the DosBox emulation. And we're also going to do the 186 on the WonderSwan, because you may not know this, but the Japanese handheld system that was competing with things like the Game Boy Color and the Neo Geo Pocket, the WonderSwan, was based on a 186 compatible processor. So I thought that would be a fun way of having two systems in this tutorial, and we would be sort of comparing the two and things. But we're going to be primarily working on a DOS system today, because we're just going to be learning the absolute bog basics of the system, learning how the processor works and about registers and things like that. Now, I'm going to be assuming you've got absolutely no experience of programming at all, so this is going to be really from the ground up. If you've covered a Z80 system or 6502, that's going to help you obviously, but I'm going to be really going from the basics, so hopefully you'll be able to get started with this even if you've no prior experience. Now, first thing, of course, if you go to my website, I have a cheat sheet available for download. This is a PDF with all of the commands in a big list. Hopefully it'll help you out, so please go ahead and grab that. I made it while I was learning this programming language, so it helped me, so hopefully it'll help you as well. Anyway, beyond that, we've got some links to some PDFs I've found helpful, but I'm going to try and, through the course of this series, explain everything I think you need to know, but obviously there'll be things I've not covered yet, or things maybe I've not covered in enough detail for you. So please go and download those as well if you're interested. But anyway, let's carry on from that. Now, the first thing we do need to discuss very quickly is the sort of concepts of decimal, binary, and hexadecimal. Now, in assembly language, we tend to use hexadecimal, and we also use binary quite a bit. Now, these are different bases, so to speak. Now, the normal numbering systems we use are called base 10, and this is typically said to be because we have 10 fingers. So a number will be either 0 to 9, that's 10 consecutive digits, and then once we go into 10, that becomes 2 digits. And so we have a 1 and a 0 then, and we've split that into 2 separate digits. Now, in a computer, the sort of core workings are working in ones and zeros, base 2. So to represent a number like 255, we would need 8 digits and they would all be 1. And that's obviously a bit inconvenient, so we tend to merge things together into something known as base 16. Now, this is quite complicated, I know. One thing I would say is there's a very simple chart here showing how decimal compares to binary and hexadecimal here. To hexadecimal, you see, we'll use digits 0 to 9, and then we'll continue A, B, C, D, E, and F here. And this allows for 16 digits in a single space of our number here. Now, the thing you want to do, if this is confusing, which I totally understand it possibly will, is try using your Windows calculator. Now, if you get your calculator just here, this is Windows Calculator, and you turn it to programmer mode, this is the Windows 7 version, but if you've got Windows 10, there's an even better one actually. And if you type in a number in decimal here, like 100, and we click hexadecimal, you'll see it's been converted to 64, and we can convert to binary and see the binary equivalent here. Now, in a lot of cases, you're not really going to have to worry too much about these things because our assembler is going to be doing the conversion for us. If we want to use a decimal number, it will convert it to what we need in the actual resulting file. If we want to do a binary number, we can do that as well, but there will be some cases you need to understand it. So I needed to just basically cover it here just to introduce you. Now, if you need to see more, I've got a dedicated video on binary, decimal, and hexadecimal, and I've got some examples and a little program I used. So please check out that video on my YouTube channel if you do need to see the real details of it, because, I mean, there'll be some things you can learn as you go along, and there might be the case that you just need a real in-depth go over of it to really get the grips of it. But as I say, for today, we're only going to be covering it very briefly. So, how does the x86 work? Well, the 8086, like all processors, has a set of registers. Now, the microprocessor is like a chip on the board, and it connects via wires, obviously, to bits of memory, and they will be the plug-in cards if you've ever built your own PC. But inside the processor itself is some tiny, tiny little bits of very, very fast memory, and these are known as registers. On an 8-bit processor, they would typically only be 8-bit, and they would just store a single byte. On a 16-bit processor, they're typically 16-bit. I say typically because the 68000 is considered 16-bit, but it's actually 32-bit registers on that system. So we only tend to have 1 or 2 of these. It depends on the system how many we have. On the 6502 we kind of have 3. On the Z80 we have a few more, and on the 68000 we have an awful lot. Now on the 8086 we have 4 general purpose mathematics registers, A, B, C and DX here. These are 16-bit, AX, BX, CX and DX. We also have some special registers, source and destination, that have some other purposes. And we have some things that are known as base pointers here. And we have some special ones which are segment registers. Now, we're going to go into those in detail later, so I'm just going to briefly mention them and move on at this point. But I did need to explain that to you. Now, the 8086 is a 16-bit processor, which means that each register can store 16 bits, and that's 2 bytes, 0 to 65535 in decimal. Now, the way it works, though, is each of those registers can be split into 2 8-bit parts, and where the register AX is referred to, the 2 parts that make up that register are AH and AL. And so we could load a value from 0 to 255 in AH and 0 to 255 in AL. But that will, of course, affect the AX register because these aren't separate registers. They're just different ways of addressing the same piece of memory. So AX is made up of the pair AH and AL. So again, we'll see all of this in an example later. I'm not going to cover segment registers at this point because they're a little bit more complex and it's more appropriate to see them when we need to know about them. So we're just going to skip over that at the moment. So we're just going to skip over stack pointers and base pointers at this point because we'll come to see them later. Now, another one that's very important is the program counter, which is called IP on the 8086. Now, this is the current byte of code that's running on our system. We're going to be writing a text file, of course, but that's going to compile to some bytes, and those bytes are going to be loaded into memory, and then the processor will tick through all of those bytes, processing them and just doing what they do. But, of course, the processor needs to know what byte it was looking at last to know what it's going to run next, and that's what the program counter does. It's the current running byte of the code. And then we've got a flags register, and this is how the processor decides what to do next. It remembers the result of mathematical operations. Did that result in a 0? Did it overflow the byte and now the data may be corrupted? It remembers things like that, and it's used for comparisons and things. Again, we'll see that in a later lesson. But again, I just wanted to give you a brief introduction of the attributes of the processor. You don't need to worry about this. We're going to cover this in a later lesson. So let's just skip all the way down here to the start of Lesson 1's content. Okay, well, just before we have a look at this, let's actually go over to our source code and let's see some programs running because I want to show you some stuff that's actually working as soon as possible. So over we go. Okay, so here we've got a very simple sample. This is a minimal file. Now you can go onto my website, you can download the sources.7-zip, and this will contain all of the assembly files you see in these tutorials. In addition, there's another file called DevTools, and this is the assembler I'm using, the emulators, and also the build scripts. And the intention is that you should be able to download all of this, put it onto your machine, and just basically use everything you're seeing here as it is, and hopefully you'll just be able to run these just as easily as I am today. That's the plan anyway, so please go on there. All of the stuff I use is free and open source, so hopefully it should all be fine for you. So this is my minimal assembly file, and I'll just go ahead and I'll press F6 here, and I'm going to select DOS VGA. And you can see here, we've got a dump of some registers, and that's this little command here, do monitor. This is a program I wrote, and it just shows the state of all the registers. It's for debugging, and we'll be using it through our tutorials, but we're not going to learn how that command works because it's a little bit tricky at this stage. So just an example there of that running. Now, as well as that, I can select the WonderSwan color here. If I just run this, you'll see the same program running on this WonderSwan color emulator just here. And how did we do that? Well, the code here and here in this header and footer are actually doing the conversion work for the two systems, and that's how we were able to run this little program on both systems. Now, the idea of this file is that if you wanted to go it yourself and just try and play around with things on your own, this is kind of a very bare minimum file for you to use as a template. Just replace this with whatever you want to do. Just leave this start and bottom bit the same, until you understand it, and then you go ahead and do whatever you want. But this is a kind of template file for you to just get started with the bare minimum for if you want to experiment on your own. Now, that said, that's not what we're going to be using today. In these tutorials, every episode has a lesson file, and that is going to be showing some very standard examples of what we can do and giving practical, visible results from the commands. That's what we're going to be doing today. So that's the source file, and now how do we actually compile that? Well, the easiest way to compile it is exactly as I just showed you. You just press F6 and select the option from my menu within the Notepad++ that I've set up. Now, what about if that doesn't work? Let's say you're not using Notepad++. Let's say you're working on a Mac or a Linux machine and you can't use that. You want to go it yourself. That's totally brilliant. If you're feeling confident, I totally encourage that. That's superb. So let's have a look at the script I'm using to actually compile the program. So here is the file that was building that DOS example, and you can see there's this long list command just here. Now this batch file is quite complex, but a lot of it's just error checks to make sure that the user hasn't done something strange that will cause us some problems. So let's go over to here and have a look at this example, which has been highlighted with the different sections, and we'll discuss those part by part just in case you're using your own assembler. So the first thing is, for DOS, we're building an executable file. We're using an exe here, and we specify that with this MZ. The next thing we're doing is we're defining some symbols. These, we'll learn a bit more about symbols later, but basically, so that my code can compile on WonderSwan and DOS, I'm having to tell the system, hey, you're compiling on DOS today. Hey, you know, you're using VGA, not EGA, because we're going to cover different graphics modes later on. So these are just some kind of pointers to say to the source code, compile yourself for this system today. So that's just something I'm using here, symbols defined on the command line. This listing file is a debugging file. It's quite handy if you're having trouble. It will show the contents of the file that was compiled and what bytecode that resulted in. It's going to be too complex for a beginner though, but it's something if your assembler does allow you to output, try and get it to output it, because it will save you later on if you start getting stuck. Of course, we need to specify a destination file, so I'm creating a file called prog.exe. You may want to create a COM file. They're slightly different, but we're going to be using EXEs in this example just because I'm more focusing on the commands and how the commands work at this stage than the actual technicalities of DOS files and things. It's much more theoretical at this stage, this tutorial. And then finally, we need to specify the source file, and this would be your lesson1.asm. In this case, because it's running from a batch file, it's %build file %. And so that's what we need to do to actually sort of compile our program. So let's go over to our source code and let's look in detail at that then. Okay, so over to this minimal file again. We're going to look at the sort of real foundations of this program then. Right, well, what do we want to look at first? Well, we're going to ignore a few of the more complex things here. The first thing is we've got an include statement here. This is attaching another assembly file. So this program is split into lots of different text files, and so we're just including a few other ones, and that hides the code that we don't want to worry about today. And this is going to be template code that will be kept compatible along this tutorial series, so hopefully these can just be left as is. The ones we really want to look at here are this call command. If you're familiar with BASIC, you'll have heard of a go subcommand, which is where you run a subroutine and then return. And assembly has the same thing. It's called a call though. And so that's just running a piece of code, and then that code will complete, and then execution will continue with the next line. So this calls a routine called screeninit. When that screeninit finishes, the IP, the program counter, will jump back to here, and then it will call the do monitor. And then when that completes, it will jump back to here. Now this line, you'll notice, is not indented. These ones have got a tab indenting them over here. This one doesn't, and there's a special reason for that. This is a label, and the colon at the end is important as well. So this defines a label, and what this is this doesn't actually appear in the resulting bytecode. This is just a piece of text that the assembler takes, and then it remembers the byte position in the file, and then any other reference to that label will be converted to that byte position. So if this was byte position 10, then this would be saying jump back to byte position 10, and it's the assembler doing that work for us. And this is a command, and that is denoted by the fact it's indented by a tab. This is a label because it's got the colon and no tab. So those labels are a text. Labels are a piece of text that the assembler converts to a number for the purpose of positions in our data. And this jump command here is a bit like your goto if you're familiar with BASIC. So where's a call goes to a subroutine and then comes back. A jump never comes back. So the jump here is jumping to that label just before, and this is, as the text suggests, an infinite loop. So it's just going to go round and round forever, never will finish. So it's just a way of stopping the program without having to worry about returning to DOS or waiting for a key or anything. Now, you wouldn't want to do that in a real system, of course, but we're using that DosBox emulator, so we can be a bit cheeky and do some things we maybe shouldn't. Okay, so let's go back to our source code for lesson 1 here. This is what we're going to be going through today. So again, you can see there's the call here to screen init, and we're just running this command called doMonitor. That will show the contents of all the registers to the screen, just so we can see what's going on. And there's a new line here which is going to move the screen down a line just to clear some space before our main code. We're now going to start looking at some very, very simple mathematical operations with those registers, because that's where we need to start with assembly. Now, I know you're going to think that this is going really slowly in this lesson, and it is, but things will start to build up quite quickly, and you'll soon realize that mathematical operations, while they seem simple and boring, are really the foundation of sprites and graphics and everything, really. So it'll build up quite quickly, but we do need to start from the basics. So the first thing we're doing here is a command called move. Now, a move command on the 8086 will take a destination and a source, and it will move the source into the destination. In this case, we're moving the value 1234 in hexadecimal, and we're moving that into the register AX. And if you remember, AX, any register with an X at the end, is a 16-bit register. And if we just get our calculator, switch it to hex and type 1234, and then switch to decimal, you can see that's 4660 in decimal. Or if we switch to binary, you can see it's this really long string here, and that's way more than 8 bits of binary, and that's why we're using a 16-bit register here. So that's how we can convert that into decimal if we need to know, and that's how we're moving. That's why we're moving it into AX, not AH or AL, because it won't fit in AH or AL. So we're just moving that into AX, and then we're running this function which I've written, and we're not going to cover it, but that's just going to show AX to the screen. Okay, well, let's press F6 here, and let's start our DOS VGA here, and let's see the result. Okay, so here at the top here is the result of the registers when the program started, and that's this doMonitor function just here. So that's before the change occurred. You can see AX was 0013. Now here we've loaded AX with 1234, and you can now see AX here is 1234. All of these are in hexadecimal here just for screen space reasons, and because that's really how you want to think in assembly most of the time. So we've loaded 1234 into AX here. Now, you remember I said that AX was a 16-bit register, but it was made up of 8-bit AH for high part of A and AL for low part of A. And we can use that, and you can see we've done that just here. Next, what we've done is we've loaded AA into AL and BB into AH. And you can see here, we did another dump of doMonitor here, and this first one here has indeed got the low part of AX, the AL part set to AA, and then the second dump, which we did just here, has got BB at the high part just here. So you can see those changes to AH and AL have indeed affected AX just here. So there we go. Now, I discussed the different bases before: binary, decimal, hexadecimal. Now, our assembler can do this for us, converting these so that we can enter the number or value that we want to use, and the assembler will figure out how that actually needs to be stored in the resulting file. So we can use decimal just by putting a number here. So 128 will be 128 in decimal. Now, because of the way hexadecimal works, that will be 80 in hexadecimal, and we've done another doMonitor command here, and that's dumped AX just here, and you can see 128 is 80. And if we think the assembler might be lying to us, we can just type 128 into our calculator here and click hex, and you can see that is 80. And if we click in binary, you'll see that's 8 bits, and just the top bit is 1. And if you start to switch between them as you're working with things, you'll start to understand more of how things are working, and it will get a bit clearer for you, although I do understand it's going to be a bit tough at the start, but it's just unfortunately the way it is. So we can use move commands to move a value into a register. Now, with these commands, the destination is always on the left of the comma, and the value is always on the right of the comma. So in this case, we're moving 128 into AX. Now, move is just transferring data from one place to another, but we of course will want to do mathematical operations, and we can do those in the same way. We've got a command called sub for subtract, and we've got a command for add, which is addition, of course. And so we can do a subtraction of hexadecimal 10 from AX, just like this. And if we do the monitor again, we've subtracted hexadecimal 10 from the 80, and that has gone down to 70, which you can just see there in hexadecimal, of course. Now, there's the fact that there's a H here, it denotes this value as 10 in hexadecimal, but we can do other values as well. If we put a B here in this addition line, we're actually adding 10 in binary. Well, let's have a look and see what 10 in binary will be. If I just type 10 here, and then I press decimal, you'll see that's 2, and it's also 2 in hexadecimal. So that's the value that we are effectively adding when we say 10B. 10 in binary. And you can see here that AX used to be 70, but it's now gone up to 72 because we've added 2 in binary. And we can just prove that if I just change this to 11. And this is really what you want to do. You want to download these files and have a play with them, change some of the values and see how the code is affected, because that's how you learn these things. That's why I'm making all these sources available to you, as well as doing them in this video. So I changed that to 11, and it's gone from 70. It used to be 72, but it's now 73. So you can see that this addition is definitely working, and the changes being reflected in this code here. Now we've done decimal here with no symbols denoting the format, so that was defaulting to decimal. A H has told us that it's hexadecimal. A B has told it's binary, but there's going to be times we're going to want to work with letters, symbols. We're going to need to print text to the screen. We're going to need to show colons between our register label and our hexadecimal value. So we're going to need to do a lot with symbols. And we can use characters just by putting them in quotes. So if we put a space in quotes here and we load that into AH, the assembler will work out what the value of the space symbol is in what's known as ASCII. And we can just see that now. So if we just run this, and we will see. Now AH is of course the top half, and that's been set to 20, and that is actually 32 in decimal. And if you know your ASCII, then you will know that that's correct. Now of course we can change that. If we wanted to do a letter A, we can just do that here. And you can see that's now changed to a 41 here. And if we get our calculator up and type in 41 in hex and change to decimal, that's 65, which is indeed a capital A. So you can see we can do that quite easily. Now in those examples we've been doing addition and subtraction to AX, and we've been using fixed values, but all of these commands will work with other registers, and both with 16-bit and 8-bit registers. So we can add AH to AL here if we want, or we could have added BX to AX. We're only using A here just for starters, but as I say, all of these are interchangeable. But you have to sort of match pairs. You can add AH to AL or BH to AL, but you can't add BH to AX. You'd have to expand it out into a 16-bit component to do that addition, but we'll cover all of that later on. But you can see here there's a wide variety of simple mathematical operations here just to get started with moving data around registers and playing with the different bases. And as I say, please download this and have a go yourself. Now we've only played with AX there, but it's time to branch out. As I said before, the 8086 has AX, BX, CX and DX, and these are the 4 main registers we would be using. There are some others, but these are the main ones. So let's do the same with BX here. We've loaded hexadecimal 666 into BX, and you can see in this next example BX now contains 666, and that was just shown to the screen by this do monitor function here. We've then moved BX into AX because remember the source is on the right and the destination is on the left. So that's been transferred across here from BX to AX, and they now both equal 666. And that's how we can work with multiple registers. Very easy. Now this is how we can move a value from one register to another, but there will be times where we actually want to swap 2 registers. Now, of course, one way we could do this would be to use a temporary register. If we wanted to swap AX and BX, we could load AX into CX and then load AX with BX and then load BX with CX, but that's going to be a bit of a pain, and we're going to use up these precious registers. We really don't have very many, so one option would be to use memory to do that, but that's slow. So we have a really nice command on the 8086 which just swaps registers around. So no temporary memory, no temporary delays using extra registers, just use 2 registers and just use an exchange command, xchg. And once again, there's 2 parameters separated by a comma, but of course there's not really a source or destination here because they're literally swapping over. So let's just see that in action just here. So here we've got 7777 in AX here, and we've still got our 666 over here. And then we did an exchange of AX and BX, so they swapped over just here. And then we started playing around with the high and low components of A here. AH and AL were swapped over. So 0666 became 6606, because you can see these two have crossed over just here. And then what we did is we swapped BH and AL, because this exchange command doesn't just work within one register. We can do the high part of one 8-bit part and the low part of the another register's 8-bit part, and that's what we've done just here. This 06 has transferred over to here, and this 77 here has transferred to here. You can see we've got quite a bit of flexibility with working with these commands. There we go. Now, we've done some addition and subtraction. We've done moving values into registers, and we've done swapping of bits of registers around. The last thing I want to cover today is a simple version of the addition and subtraction. Now, we're going to cover loops later on, but of course in programming, if you've done basic before, you'll do your sort of for I equals 1 to 10 loop, and I will go up by 1 each time. Increasing by 1 is going to be a thing you're going to have to do an awful lot, and while you could of course do add 1 each time or sub 1 each time, that's a relatively large command. It compiles to 2 bytes, I believe, so that's going to be taking up a little bit of memory and a little bit of processing power. And while the 8086 is very fast by the comparison of the Z80, we're still going to want to be as efficient as possible, especially because the processor has some memory limitations, which are going to be a bit of a pain to us. So we want to make our code as small and as efficient as possible wherever we can. So rather than doing an add 1 or a subtract 1, we've got some special commands which you'll know if you've used other systems: inc and dec. So inc increases a register and dec decreases a register by 1. So these are the way that it's quickest to increase the value by 1 and decrease the value by 1. And these are what you would use in your loop when you're increasing the value, or when you're reading banks of memory and you're moving across 1 each time. These are the options available to you. So they're very simple commands. They work on all registers. So you can see here we had 6677. We did an inc and that became 6678. And we had 0677 here, and we did a dec of BX and that went down to 0676 here. Now, of course, these aren't just limited to 16 bits. We could do dec BH as well, if we just run that, where you can see now that the H part has gone down by 1 as well to 05, so both parts have now gone down by 1. As I said before, I'm sure you're having a lot of fun watching this, and I totally encourage that. I'm going to have loads more of these coming up, but really if you're actually planning to program these yourself, you're going to want to create some code of your own or modify this one. So that's why that minimal example is there for you. And that's why you can download this lesson, and you can do the kind of thing I've just shown you there. Have a play around, change things, see what works, have a go. That's really what the fun of this is. You should be having a play around and learning things yourself. So we've covered a lot of stuff in this lesson. I know it's we've not gone into massive detail here, but I wanted to give a good quick lesson with a fair amount of stuff that wasn't too overpowering for you. Now, all of the content that we've covered in this video, of course you can get the source code, but there's also a companion text tutorial that matches the same content with visual diagrams on my website, so please go and have a look at that if you want more information. As I say, download the development tools, download the sources. I also now have a forum where you can discuss assembly programming, and I'll try and help you out if I can. I have a Discord now, so you can chat with people who are interested in programming. So yeah, please take a look around all of the options I've made available and find what works for you. Please like and subscribe. Subscribe to my channel and give the video a like, because it takes a lot of work making these and it's a real encouragement for me. Anyway, I hope you've enjoyed this. I hope this has given you some interest in x86 and given you some encouragement. I know we've not covered much today, but we're really going to go through it pretty quickly, and you'll find in just a few lessons we'll be putting graphics on the screen and making a little game or something. So don't think that just because we've not made very much progress today it's going to really build up, and I hope you're going to enjoy it, and I hope you're going to stick around and watch it. Anyway, I hope you've liked what you've seen today. If this seems something that's interesting to you, but you prefer something else, have a look around my YouTube channel, because I've already done 8086, 6502 and 68000, and I've covered tutorials on all of the major systems really that use those processors. I've done Amiga, Amstrad CPC, C64, NES, Famicom, PC Engine, Genesis, you name it. I've covered all the major ones, and I've got more I'm planning to do in the future. So if this doesn't quite look like what you had in mind today, take a look around and see if there's something else you like more. Anyway, I hope you enjoyed this anyway. I hope you're going to enjoy playing with the 8086, and I hope you're going to enjoy programming in general. Thanks for watching today, and goodbye.